Hello students, good evening. So welcome to the session 14 of work, energy and power chapter. So in this we are in the middle of discussion about the collisions, correct? So in the previous class, we were looking at the various types of the head-on collision. Okay, today our focus will be on covering of this oblique collisions. Okay, so in oblique collision also we are going to see these subcategories, right? What will be the subcategories we'll have? We'll be having the oblique perfectly elastic, oblique inelastic situation, and then we'll be having oblique perfectly inelastic. Okay, so we'll see what happens in each of these type of collisions, what kind of questions we can expect in them. We'll try to cover as we go on. Okay, but before that, we need to understand what is the fundamental difference between a head-on collision and an oblique collision. Okay, so head-on means, remember what we said, the particles or objects which are involved in the collision, their velocities will be confined to a line. That is what we said. Remember, what is it? In case of the head-on collision, what happens? The velocities of particles will be confined to a line. Why that happens is, at the time of collision, if you look at these two objects, their contact surface, we can draw the normal to the contact surface. Okay, so what will be the normal? The normal that you draw for the contact surface is also, by the way, called as a common normal. Normal that you draw to the contact surface is called as what? Common normal. The impact of the collision, which is our impulsive forces, the impulsive forces will be acting along that common normal. So in which direction the impulsive force will be acting? They will be acting along the common normal. So as a result of it, as a result of the impulsive forces or the collision forces, whatever we call it, the velocities of the particles might change, but still after the collision also they will be confined to the same line. After the collision also the velocities will be confined to same line. Their values might change. Maybe they may change the direction of motion itself sometimes, but they will still be confined to the same line. Why? Because the common normal, that is where our velocities will be aligned. When it comes to the oblique collision, we are going to see something different. Okay, so here the important point about the head-on collisions is what? When you look at the macro objects colliding, we can see that contact surface, you can draw the common normal. The velocities of the particles will be confined to that common normal direction. So whatever the impulsive forces impact, that may change the velocities magnitudes, that may change the direction of velocities. Means, if the particle is moving to the right initially, it may sometimes be changed to move to the left side after collision. But the velocities of the particles before the collision as well as after collision, they will be confined to that same common normal line. That is what we see as the characteristic of the head-on collision. Okay, and that is the reason why, even remember, when we talked about the coefficient of restitution, we said the coefficient of restitution is more meaningful when we use in the case of the head-on collision. Why? Because coefficient of restitution, it is a measure of the effect of these impulsive forces. So it is a measure of the effect of impulsive forces, because the impulsive forces are acting along the same line of the velocities, So when you measure the coefficient of restitution, how do we measure in the case of the head-on collision? It will be what? Relative velocity of separation after collision, v2 minus v1, divided by relative velocity of approach before the collision, which is u1 minus u2. So all these velocities are confined to the same common normal line, which is the direction where these impulsive forces will be acting. So that is the reason why this coefficient of restitution will be more meaningful when we use it in the analysis of the head-on type of collisions. Okay, now we will go into the discussion about the oblique collision. So what happens in case of the oblique collision? Okay, so today, right, we are going to focus on the oblique category. In that we are going to see what perfectly elastic oblique, inelastic oblique, and then perfectly inelastic oblique collision. So perfectly inelastic can be also called as what? Plastic. Oblique collisions, right? One of the characteristics that we will be able to see is the velocities will not be confined to a line. Okay. When we say that velocities are not confined to a line, we have to consider all the velocities. Velocities before, velocities after. Some of them may be in one line, but some of them will be definitely in a different line. That is what is the characteristic of the oblique collision. Why the word oblique? So by the way, oblique collisions, right, they can be either a 2D type or a 3D type. If the velocities are all in a plane, right, we can call it as a what? 2D, because head on we will call it as one dimension collision. Oblique we can say either it is a 2D collision. When velocities are all in a plane, we can call it as a 2D. If they are in spatial distribution, means we can call it as a 3D, like that. Okay, but this doesn't have much importance. Calling it as a 2D or 3D does not have much importance. Okay, main thing is what? The velocities will not be confined to a single straight line. That is what is the most important thing about the oblique collision. Okay, now we will see even why do we call it as a oblique collision. Let us look at the basic of the oblique collision. Take for example, this is object 1, object 2. These are like the spherical bodies. They are coming and colliding. You can see here clearly this is that contact surface, right? And we can draw the normal over here. This is our common normal. What is this? This is the common normal. Now what happens in case of the head on? The velocities of the particles, if you look at the velocities of the particles before the collision, let us call them as maybe u1 and u2, like that. They will be confined to that same common normal line. That is our head on discussion. So as a result, right, after collision velocities v1 and v2 also will be confined to that same common normal line. But here in case of oblique, that is not going to happen. Means what? We may have the velocities in different orientations. Let us say this is having a velocity u1, this is having a velocity u2. So that the name oblique means what? Remember in projectile motion, the projectile that we project making an angle theta with the horizontal, what do we call it as? We call it as oblique projectile, right? Why the word oblique? Oblique means making an angle. So here the velocities will be making an angle with the common normal. That is the reason why we can call them as what? Oblique collision. The velocities will be, in case of head on, right, the velocities will be along that common normal line. Here the velocities will be making an angle with the common normal line. That is why we call it as what? Oblique collision. Now the impulsive forces, in which direction they will be acting? They will be acting along the common normal. So this is the very important point about the oblique collision. You see the velocities of the particles, right, we can take them into components. How we can take them into component? The components which are parallel to the contact surface and the components which are perpendicular to contact surface, means that is along the normal line. Okay, so we can take the velocities of the particles that are colliding into components. What are the components? One is the components parallel to the contact surface. Other components are what? These are two. We can resolve them into the two perpendicular components. One is component parallel to the surface. Second is what? The component along that normal line. Impulsive force is acting along the normal line. So no change. Okay, so what is this very important point about the oblique collision? No change in the velocities along the surface. So we are taking the velocity components, right? The components which are along the surface are parallel to surface. Those velocity components will not be changed during the collision. Why? Because the impulsive forces are not acting along that direction. Impulsive forces are acting along the common normal line. So there will be no change for the velocity components of the particles which are along that contact surface. This is one very important point about the which one? The oblique collisions. The velocities, if they are changing, means there will be only change for the components which are along the normal line. The change in the velocities rate can be seen only for which component of velocities? The component of velocities which are along that normal line. Okay. Now what we'll do is we will look at how we will define the coefficient of restitution, because here also we can define the coefficient of restitution. Whenever there is an impact of that impulsive force, right, we can measure the impact of that impulsive force by using this coefficient of restitution. Okay, see how we are going to define the coefficient of restitution. But before that, right, the impulsive force or the collision forces, right, they will be acting along the common normal direction, means their impact will be only along the direction. So here the coefficient of restitution is defined as the relative velocity of separation. Only we have to consider the normal components, means the components of the velocities along the normal line. Means what? Look at this, V2. So previously what is the formula we had? V2 minus V1 by U1 minus U2, right? Here the thing is, we consider the final velocity of the particles, their components along the normal line, divided by the U1 minus U2, but this is not the total U1 and U2 values. These are what? The component of U1 along the normal line minus component of U2 along the normal line. So we have to consider as it is formula, but the only difference is what? The V2, V1 are not the total velocity values. These are what? We have to take all these velocities, right? U1, U2, V1, V2. We just have to take their components along the normal line. So the relative speed of separation, that is after the collision, the value has to be taken only along the normal direction, divided by the relative speed of approach. That also we have to take only along the normal direction. Why? Because the components of velocities which are parallel to the contact surface, right, they will not have any change. They will be as it is. Whatever the values before the collision happening, right, after collision also those values will not change. Okay, so this is the characteristic of any oblique collision. And like every collision, right, conservation of momentum will be satisfied, because collision is after all what? It is a independent event, right? Like head on also, oblique also, conservation of momentum equation will be satisfied. Now what kind of questions come, because we will go into the details of it. Like we are going to see oblique, we have subcategories, right? Oblique, perfectly elastic, oblique, inelastic, oblique, perfectly inelastic. We will see all those things, but before that we can even sometimes expect questions straight based on the use of the conservation of momentum principle, because conservation of momentum can be used for any type of collision, whether it is a head on or oblique. Okay, so let us look at this. If you have a question like this, right, mass m moving horizontally along the x-axis with a velocity v collides and sticks, means it is colliding and sticking, to a mass 3m moving vertically up along the y-axis with velocity 2v. Means look at this, m is moving with a velocity v horizontally along the x-axis, means we can say it is what? V into I. The other one, 3m, is moving along the y-axis with a velocity 2v, we can say it is what? 2v into j. After collision what is happening? They are sticking and moving, they both are sticking and moving together. They are asking us what is the final velocity of the combination. What they are asking us what is the final velocity of combination. Can you tell me the answer? It is straightforward, right? What are we going to do? We don't know what is the velocity. Let us say v is the velocity of that combined mass, that is sticking and moving after the collision. So here what is the this is an oblique collision, right? Because look at this, the initial velocity of the m is what? Along the x-axis. The initial velocity of the 3m is along the y-axis. They are not moving in the same line. This is an example of the oblique collision. But this can be solved just like that by using the conservation of momentum principle. Why? Because that can be used for any type of collision. So what is it that we'll have? Initial momentum means m into so the final velocity, let us call it as what, some v1, so that we'll see the difference. So m into initial momentum is what? Momentum of that mass m is what? M into vi cap. What about the momentum of 3m? 3m into 2vj, that is the total initial momentum. Final momentum means this is m and 3m moving together. Total mass is what? 4m, right? 4m into v1. This v1 is what we are looking to find. We are looking to find what is the v1 value, right? So on both sides we can cancel m. If we cancel means what do we have? vi plus 6v into j, that is equal to 4v1. We are looking for v1, right? Bring the 4 to the left side. So what is it? It will be what? 1 by 4 into vi plus 6vj, that is equal to what? 1 by 4 into v into I plus 6 by 4 means what? That is 3 by 2. Check it. What is the answer? 1 by 4 vi plus 3 by 2 vj. So we are able to get the answer just like that by using the conservation of momentum principle. Okay, so conservation of momentum can be used for head on as well as oblique, and in this also for each and every subcategory, whether it is an elastic or a inelastic or perfectly inelastic, whatever it is, right? Always, since collision is an isolated event, we can apply the conservation of momentum principle. Okay, like that we can have some very basic questions. Let us look at what is this perfectly elastic in the oblique category. Okay, this is the fourth. Why? Because 1, 2, 3 are what? Already we covered. 1, 2, 3 are what? In the head on type. Head on elastic, head on inelastic, head on perfectly inelastic. Those 3 are over. Now we are looking at the fourth category. What is it? The perfectly elastic type in the oblique collision. Means here already we said, right, we will be able to use what? We will be able to use, we will be able to use the conservation of momentum, because that is there for all the type of collisions. Apart from that, we will also be able to use this equation. What is this? The conservation of kinetic energy of particles. Whatever the initial kinetic energy, right, half m1 u1 square plus half m2 u2 square will be equal to final kinetic energy of the particles. Other than this, because here we'll have many variables. Why we'll have many variables? You know, because the velocities, if you look at it, the velocities of the particles, right, they may be in different orientations like this v1 and v2. So we will look at what is the corresponding angles. Let's say this is the common normal line. What is the angle made by the v1 with the common normal? Let us say alpha. Here what is the angle made by the v2 with common normal line? That is what? Beta. So we'll have alpha and beta. Since it is perfectly elastic, the E value will be equal to 1. But here what do we need to keep in mind? That E will be only defined for the components of velocities along the common normal. E will be only defined for what? The components of velocities along the common normal. What is it? The v2 normal component minus v1 normal component divided by what is it? u1 normal component minus u2 normal component. Okay, so the coefficient of restitution is only defined for the normal components of the velocities, and already we said the components of velocities along the contact surface, they would not change. The components of velocities along the contact surface, they will not be changing. Okay, so as such, solving these questions, right, we are going to involve multiple equations. See, we'll have conservation of momentum. This equation, E value, this is equal to 1, and we will also have an equation coming from the balancing of the velocity components. Okay, so the overall solution for the velocities in case of the oblique collision, right, it might look little bit complicated at times, but the thing is, when you are getting to questions, right, we will see that they will not give a question on solving the entire part of it. They will be asking us questions on certain segments. We'll see when we go to questions, we'll be able to understand. Okay, so if you want to completely solve the velocities with directions, means we have to use these equations. We can use conservation of momentum, we can use the conservation of energy, we can use the quotient of restitution value, and we can use the idea that the velocities of the particles along that contact surface, they will not change, they will remain as it is. So these are the things that we can use to solve problems in perfectly elastic oblique collision. But how do we use these things, we will be able to know when we go to the problems. Okay, let us look at a question like this. On a frictionless surface, a block mass m moving with a speed v collides elastically with another block mass m which is initially at rest. Means what? This block m moving with a velocity v is moving and colliding another one which is initially at rest. Okay, after collision, the first block moves at an angle theta to its initial direction. Means the initial direction is this, right? It is moving in which direction? At an angle theta with a speed v by 3. With how much speed it is moving? V by 3. The second block speed after collision is, means second block may move in some direction. Okay, here what they are asking, they are just asking what is the speed of the second block after the collision. Okay, so here this is an elastic, right? This is oblique collision. We can see after collision the we can number them, right? 1 and 2, like that we can number. The first block is going at a different direction, right? It is oblique collision, it is not head on. Here we are, second block might go in some direction, we don't need to worry about it. They are just asking us what the velocity of this, let us call it as v dash. They are asking what is the velocity of that second block. So how we can solve it? Think about it. They're just asking us the value of it, right? How we can find out the value? We know the object 1 initial velocity mass. Object 2 initial velocity is what? 0, because that is at rest. They are saying, right, what is it? Same mass which is initially at rest, means this is at rest, velocity 0. Finally, that first block is having a velocity or speed v by 3. They are asking what is the final velocity or the speed of that second block. Can we simply use conservation of energy, conservation of kinetic energy? Yes, right. Why? Because this is elastic collision. That is what I said. We have various tools that can be used when it comes to oblique elastic collision. Conservation of momentum, conservation of energy, kinetic energy of particles, quotient of restitution which is equal to 1, and then the idea that the velocities of the particles along the contact surface will remain the same. So here they are not even giving us in what way these blocks are colliding, so we don't have an idea about the contact surface. But here you can see this question can be easily solved by straight away applying the conservation of kinetic energy of particles. How? Initial kinetic energy means what? Half into m into v square for the particle 1. Particle 2, what is it? 0. Final kinetic energy means particle 1 is what? Half into m into v by 3 the square, because the speed is what? V by 3. For the second particle, we are saying it is moving with a velocity or speed v dash, right? So the kinetic energy will be what? Half into m into v dash the square. So we can see on both sides, right? Half m we can cancel off. Straight away we can cancel off half m, right? That is it. We will be able to get the answer. Check it, guys. You can tell me what is the answer if you are able to get it. What is the answer we can get here? Left hand side, what do we have? V square, right? Is equal to right hand side. V by 3 the square means what? V square by 9. Then v dash square. So v square minus v square by 9, that is v dash square. This is what? 8v square by 9, that is v dash square. Means take a square root of 8v square by 9, that is our v dash. What is square root of 8? Means 2 root 2 v. What is square root of 9? Means 3. So 2 root 2 v by 3, that is our v dash. So you see here this question, right? As I said, we will have to see which of these relations we have to use in the particular condition. So here we are able to get the answer by using what? By using the conservation of kinetic energy principle. We are able to straight away use it. So only when you do some practice we will be able to see, because here, right, the idea of coefficient of restitution or the idea of velocities of particles remaining same along the contact surface, those and all cannot be used, because they didn't even say in what manner these blocks are colliding. Block means it may be cubical, right? So how they will collide, it depends. No, so they are not giving any information about it. So the thing is, we will be able to get the answer by using simply conservation of kinetic energy of particles. Okay, so this is one kind of question. Let us look at another one. A particle strikes quarter of a circular disc. So this is a circular disc, okay, quarter of the circular disc, it is striking it, and rebounds elastically. Means what? It is undergoing the elastic collision here. The angle by which its velocity vector is rotated, it is rebounding. After collision, it is what is happening to it? It is rebounding. They are asking what is the angle by which its velocity vector is rotated. So can you see how the rebounding will occur? Can you tell me the answer for this? For that, what I will do is I will just redraw the diagram over here so that we will be able to see. Okay, this is our quarter of the circle. It is hitting at a point making an angle theta. Okay, I'll use different markers so that we can see clearly. So it is coming like this. It is coming along this line with a velocity v. So this is the initial velocity direction. They are asking us what? The angle by which its velocity vector is rotated. So here the initial velocity vector is like this, what? To the left side, horizontally. Okay. Now we can draw the at the point of contact, right? We can draw the normal. So what will be the normal? This is the normal, right? This is the normal. Okay. Now remember, what is it that we said in case of the elastic? This is an oblique collision, right? The velocity along the contact surface means, we'll see here. This is the contact surface. Tangential. Contact surface means what? Tangential. Okay. The initial velocity, we can take the components. How we can take the components? Look at this. This is the component of the initial velocity, which is parallel to the contact surface. This side will have the component of the initial velocity along the normal. So it is like this, right? We take the components means tangential it will go, and normal it will be towards the center. Remember, what is the thing that we said? The velocity of the particle along the contact surface will not change. Means this is going to be as it is, because it is hitting, right? It is hitting the surface. The impact force will be along that normal direction. So after collision, what is going to happen? The particle is going to bounce back. The particle is going to be basically what? It will be bouncing back. Okay. So it will bounce back with the same value of the velocity. It will change the direction, but velocity will be same. This is what we will see. Okay. Now by symmetry principle, right? This is symmetrical, no? If you look at, say, this is theta, right? It is theta. So the angle here is theta. the final velocity after it is bouncing back, by symmetry principle it will be what? If the initial velocity is making an angle theta, means the final velocity also will make the same angle theta. This is the final. The final velocity also will make the same angle theta with the common normal. Now look at it. They are asking us what the angle by which the velocity vector is rotated. Means this is the initial direction. The angle by which it is rotated. Initially is like this. Finally is going like that. So the angle by which the velocity vector is rotated. That angle we need to find. How do we find it? Look at this. The angle by which it is rotated. How do we get it? Over here, right? Look at this line. It is a straight line, right? The angle. So let us say this is a delta. Delta plus here it is a theta. Another theta. Total angle is what? Angle on a straight line, which is what? Pi, 180. Means delta plus 2 theta is equal to pi. Means delta will be equal to what? Pi minus 2 theta. So we can expect some kind of questions like this, where it is not just about getting the velocities. It's also about understanding how, in case of the oblique elastic collision, the directions of the velocities will get modified. Okay, so remember the point is what? At the time of the collision, the velocities of the particles along the contact surface will not change, because the impulsive force will not create any impact in the direction. Only the impact will be on the components of velocities along that common normal direction. That is one important thing. Okay. Now the second thing is, like the way we discussed in the case of those what is it, the head-on type, right? If you have a heavy object, in whichever case the heavy object is there, like in this case the quarter of the circular disc, it's like the heavy object, or a rock or something, heavy object is there, means the collision will not be able to change the velocity of the heavier objects. Even we have seen this with examples also, like a lorry coming and hitting a person going on a cycle. Okay, or we bouncing a ball. Earth is the heavy object. So during the collision time, right, the heavier object means it is not like m and 2m. If one object is having a mass m, other is having a mass 1000 m, like that, the heavier object, right, will not see any impact on its velocity due to the collision. Okay, so these are some of the things that we need to keep in mind in whichever type of collision it is. Okay, so the answer for this question is what, guys? It is our option C. Okay, so now we'll go to the next question. Look at this one. What is this question? There is a wedge. Wedge means what? The inclined a plane kind of a thing, that is sometimes we can call it as what? Wedge. There is a wedge which is moving with a velocity v. Okay, so it is moving with a velocity v horizontally, undergoing elastic collision with the ball. So there is a ball which is kept hanging with the help of a rope or something. It is undergoing what? Elastic collision with the ball. Find the velocity of the ball after the collision. What we need to find here? We have to find what is the velocity of the ball after the collision. This is what? A case where small m, which is the mass of the ball, is very less in comparison to capital M. Small m is what? It will be very less in comparison to capital M. We have to find what is the velocity of the ball after the collision. So remember, this is initially at rest, right? So when it is having collision, the impact of collision will be only along the normal direction. Means if it is having some velocity after collision, means it will get the velocity in which direction? Along the normal direction. It will get the velocity along which direction? Along the normal direction. Correct. What we'll do is we'll look at the, so when it is about to collide, this is the normal direction, right? That is the normal. Okay. Now we can think of the velocity of the wedge components. This is alpha, means this is alpha, right? So this will be alpha. Okay. So what is it that we'll have? The velocity of the wedge, we can take it into two components. The component along the normal is what? V sin alpha. Component along the contact surface is what? V cos alpha. So first we have to get what are the, so it is like this, alpha is here, so V cos alpha will be along the contact plane, V sin alpha will be along the normal direction. Okay. Now since the mass of the edge is very small, wedge mass is very high in comparison to mass of the ball, so after collision the wedge velocity will remain the same. After the collision, the wedge velocity will remain the same. Why? Because that is a heavier mass, right? It is like the heavy object. Its velocity will not be impacted by the collision. Now we need to find what is the final velocity of the ball after the collision. So if at all it is having some velocity, what are we saying? It will be moving along that normal line, isn't it? It has to move along the normal line. So I'll just represent whatever is required for us now. Okay. So the velocity of the wedge along the normal direction is what? V sin alpha. Before the collision also it will be same. After collision also it will be same. Why? Because the wedge is a heavier one. Its velocity will not be impacted. Okay. Now the ball, let us say, is starting to move with a velocity some v dash. It will be moving along that normal line. It will be moving along the normal line. So how do we find that v dash value? Remember, if we want to relate the velocity components along the normal line, first thing that will strike our mind is what? Coefficient of restitution. First thing that will strike our mind is what? Coefficient of restitution, right? Look at this. The wedge initial, this is before the collision. Initially, wedge is having a velocity v sin alpha in the direction. The ball is at rest. Means along the normal direction, what is the relative velocity of approach? Means this is like the particle 1, particle 2. What is the relative velocity of approach? Means u1 minus u2. We are only considering along that common normal. What is it? u1 minus u2 means what? V sin alpha minus 0. That is V sin alpha. That is our u1 minus u2. After collision, the wedge, it will still have the same V sin alpha. Particle 2 might move with some velocity v dash. That v dash is what we are trying to find. So what is the relative velocity of separation after collision? Means that is v2 minus v1. What is it? V dash minus V sin alpha. v2 minus v1. Okay. But it is elastic, right? Elastic means what? The relative velocity of separation after the collision divided by the relative velocity of approach before the collision. Everything has to be taken along that common normal direction. Okay. The quotient of restitution is what? For a perfectly elastic, it is what? 1. Means the V2 minus V1 by U1 minus U2 is equal to 1. Means what? V dash minus V sin alpha is equal to V sin alpha, which means V dash is equal to what? Take it to the right side, that also becomes plus. So 2V sin alpha. So after the collision, right, this ball will pick up a velocity of how much? 2V sin alpha along that common normal. Okay, so here what are the things that we are using? Understand this carefully. What are the things we are using? We are using first condition. What is it? The wedge is a heavy one, so its velocity will not be impacted by the collision. It will be as it is. Then we are looking at the quotient of restitution along the normal direction. Why? Because that is where we will measure the quotient of restitution in case of the oblique collision. So we are looking at what is the velocity component for the wedge. Initially also it will be same, finally also it will be same. Why? Because the velocity will not be impacted. V sin alpha. After the collision, if the ball is picking up velocity, means it can pick up velocity only in that direction, isn't it? Because the impact of collision is only along the line, right? It will be getting velocity only along the common normal. So we are calling it as V dash, and by using the E is equal to 1, we are able to get what is the velocity of the ball after the collision. You see, it will be moving with what? 2V sin alpha. It will move with a velocity of 2V sin alpha. Along that, this is our normal line. Okay, this is our common normal direction. In the direction, it will move with a velocity of what? 2V sin alpha. What is the answer for this, guys? What is the answer? It is option D. Okay. Now let us look at the inelastic oblique. Inelastic means what? The E value will be in between 0 to 1. Inelastic means what? E will be between 0 to 1. But here also E will be defined only for what? E will be defined only for, so this is the contact surface. And we will use a different color so that we can see it clearly. So this is our, this is what? The common normal direction. So in case of inelastic oblique collision, the things that we need to keep in mind are what? The velocities of particles along the contact surface. The velocities of particles along the contact surface will not change. This is an important thing for all the oblique collisions, because the impact of collision will be only along the common normal. And along the common normal, what is the thing that we will use? E value we will use. E will be between 0 to 1. But for any type of collision, here we cannot use conservation of kinetic energy of particles. We can use, what we can use? Conservation of momentum we can use. Because for any collision, conservation of momentum will be satisfied. Okay, so we will see some examples what kind of questions can be asked. A ball mass m hits the floor with a speed v0, making an angle of incidence alpha. This is alpha. Okay, make an angle of incidence alpha with the normal. Okay, so how is it hitting? It is hitting the, so this is the floor. It is hitting the floor with a velocity v0, making an angle alpha with the normal. So this is the normal. This is what? This is our normal direction. Okay. The coefficient of restitution is E. Find the speed of the reflected ball. What is the coefficient of restitution is what? E. So here quickly write, the ball is coming with a velocity v0 by making an angle alpha. So this is alpha, means the angle here will be what? Alpha, vertically opposite angles. If you take the v0 into components, the component along the normal is what? v0 cos alpha, that is pointing down. The component which is parallel to the surface is what? v0 sin alpha, remember one thing, this value will remain the same. Why? Because the impact of collision will not be affecting that value. Impact of collision will not be affecting that value. That will be remaining as it is. Only what will be changing when it is bouncing back means the normal component of velocity will be changing. What will be changing? The normal component of velocity will only change. It will be now pointing up. Let us say the value is v. Okay. They are asking us what? Find the speed of the reflected ball. Means we have to find the total. It will have the component of velocity which is parallel to the surface remains unchanged. V naught sin alpha. The component of velocity along the normal direction is going to change. How much it will have a final value? Look at this. E they are giving. Remember in oblique collision, what is E? E is representing what? Relative velocity of separation after collision. Here the floor is remaining as it is, right? By what velocity the ball is separating from the floor along the normal line? V. Divided by relative velocity of approach along the normal line. What is the velocity with which it is approaching? V naught cos alpha, right? So E is equal to what? V, which is the relative velocity of separation along the normal line, divided by V naught cos alpha, that is the relative velocity of approach before the collision along that normal line. So from here, right, if you rearrange, E into V naught into cos alpha is equal to V. That's it. We get the V value. They're asking speed. Speed means what? After getting reflected, it has got two components of velocity, right? One is the parallel to surface. Other is the one that is along the normal line. So total speed means what? It's like it has got x component, y component. Total speed means what? Root of x component square plus y component square, right? Means what is it? V naught square sin square alpha plus what is this? E square V naught square cos square alpha. That is the total speed. Means what is it going to be? We can simplify and write it. So from there maybe we can take the V naught square out, because V naught square if you take it out means it will come out as what? V naught. It will be coming out as what? V naught, right? So look at this. We can write it over here. The speed of the reflected ball is what? V naught comes out. Root of sin square alpha plus E square cos square alpha. So this is the speed of the reflected ball. So here you need to be clear. What are the things that we are using? We are using the idea that velocity of the ball after collision along that contact plane will remain as it is, remains unchanged. That is one point. Second thing that we used is coefficient of restitution. Second thing that we use is what? Coefficient of restitution. Okay. So this is about the kind of questions we will be able to see in case of the inelastic oblique collision. You have to confirm, guys, whether you are able to get the answers or not. Next, look at this one. A ball with a mass 1 kg strikes a smooth horizontal floor as shown. How it is striking? Look at this. This is the mass. It is coming like that and then striking here. This is what? This is the contact surface. Okay. Where is that normal to the contact surface? You can draw here. This is the normal. That's the normal, right? Okay. The impulse exerted on the floor is, means we need to find what is the impulse that is exerted on the floor. So how do we find the impulse exerted on the floor? Think of it. Because this is oblique collision. They didn't even say whether it is an elastic or inelastic. But since it is making a different angle after reflection, right? So after reflection it is making a different angle. Already we talked about it, right? If it is elastic means it will be symmetrically going. If it is making a different angle means what? This is the case of inelastic. This is the case of what? Inelastic. Okay. But they did not give us what is the velocity with which it will go. We'll see how we can find it. Okay. So we'll see, first thing is what we have to find the impulse exerted on the floor, means whatever is the impulse that is experienced by the ball, because impulse is action reaction pair, right? Whatever the impulse acting on the ball, the same amount of impulse value wise will be acting on the floor also. Same amount of impulse will be acting on the floor. So to know what is the impulse acting on the ball, what is impulse force means the change in momentum, right? What is impulse force means change in momentum. We know the velocity components along the contact plane will remain the same, they will not change. Only the velocities along the normal line will change. See how we can do it. Let us say v is the velocity of the mass m after the collision. Okay, now what is the component of velocity along the contact plane? It is what? V cos 37. So we are looking at components along the plane. For the final velocity, we are saying it is v. We don't know what is it, we have to get it. The component of velocity along the contact plane is what? V cos 37. By the way, what is cos 37? 4 by 5. I hope you guys remember these two relations. Cos 37 is what? 4 by 5, and cos 53 will be what? 3 by 5. Okay, so these two things we have even used. Before the collision means, look at this. The 5 meter per second direction is like this, right? This is 53, means this also will be 53. So what is the component? 5 cos 53. So what is it? V into cos 37 means what? That is 4 by 5 is equal to, right side is what? The 5 into cos 53. What is cos 53 means? 3 by 5. Okay, so what is it that we have? 5 will get cancelled. So V is equal to what? 5 3s are 15 by 4. That is the V value. So what is the velocity after the collision, right? What is the velocity for this? 15 by 4. How are we able to get it? We are able to get it by using the idea that the velocity of the particle along the contact plane will remain the same. That's it. What is the idea we are using here? The velocity of the particle along the contact plane will remain the same. Okay. Now we are done with first part. But this is not what they're asking. They're asking us what? The impulse exerted on the floor. That is what they're asking. So how do we calculate what is the impulse that is exerted on the floor? For that, what we said, we will look at what is the impulse that is acting on the ball. Okay, so how do you get the impulse? Change in momentum, right? So anyway, the velocities along the contact surface are not changing, right? So we will only look at what is the momentum change that happens along the normal direction. So look at this. The initial velocity 5 meter per second, its component along the surface is what? 5 into cos 53. Already we saw that. What about the component along the normal? 5 into sin 53. Okay, so the initial momentum along the normal direction is what? Mass of the body is 1 kg into the speed is what? 5 into sin 53 means what is sin 53? It will be 4 by 5. We will take this direction as minus j cap. Why? Because it is downwards. So what is it? 5 is cancelled. So meter per second, that is what? Minus 4 j cap kg meter per second. We can also write it like what? kg meter per second can be written as what? Newton into second. Okay, so that is minus 4j Newton into second. That is the initial momentum of the ball along the normal line. This is 37, right? So it will be what? 53. What is the final momentum along the normal line? Look at this. Normal line is what? Mass is 1 kg into 15 by 4 cos 53 will come. So 15 by 4 cos 53, that will be upwards, means it will be what? J cap. What is cos 53 means? 3 by 5. What is cos 53 means? It will be what? 3 by 5. So look at this. 15 by 4 into 3 by 5, right? So 5 ones, 5 threes. That is what? 9 by 4 into J cap. That is also Newton into second. Now change in the momentum means what? Final minus initial, right? Impulse acting on a body will be equal to what? Change in momentum for the body. Because here we are looking at only change in momentum along the normal line. Why? Because along the contact surface there will be no change in momentum for the ball. So the impulse acting on the ball will be equal to the change in momentum for the ball along the normal direction. So impulse acting on the ball will be change in momentum along the normal direction, means final value minus initial. So what is it? 9 by 4 j minus initial is what? Minus 4j. Totally what is it? Minus minus becomes plus. So 9 by 4 plus 4 into j. That is the direction of the impulse. Okay, but here in the answers if you check, means they are only giving us the value. Okay, the impulse will be acting in which direction? On the ball. On the ball the impulse will be in which direction? It will be along the j cap, means it will be in the upward direction. But here direction is not required, just the value is required. Okay, so 9 by 4 means what? What is 9 by 4 means? 2.25 plus 4, what is it? 6.25. 9 by 4 means what? 2.25, right? So 2.25 plus 4 means 6.25. That is the impulse acting on the ball. Now because the impulse force is internal force, right? Means whatever is the impulse experienced by the ball will in return exert the same amount of impulse on the floor. In return the ball will exert the same amount of impulse on the floor. Okay, so this is how we look at the questions on the inelastic collision in case of the oblique category. Now we look at the sixth type. What is it? Perfectly inelastic oblique collision. Remember here E value will be equal to 0. E means what? V2 along the normal direction minus V1 along the normal direction, means this will be 0. So after the collision, this is very important, because generally what we think is perfectly inelastic. This can be also called as what? Plastic. We will have a notion. Perfectly inelastic means, because this is what we will hear in a lot of places. Perfectly inelastic means the object will stick and move like that. In case of oblique collision, they need not stick and move, because the basic idea of perfectly inelastic collision is what? The kinetic energy loss has to be maximum, and that will happen when E is equal to 0. E is equal to 0 means what? The V2 along the normal direction will be equal to V1, means after the collision the components of velocities along the normal direction, the components of velocities along the normal direction will become equal. Components of velocities along the normal direction. Look at this. This is the contact surface. This is our normal direction, right? The components of velocities along the normal direction will become same after the collision. That does not mean that they will move together, right? Why? Because if their velocity components parallel to surface are different, then will they move together? They will not move. So here we can look at this as a condition. What is it? If you want to have moving together the objects have to move together, that kind of situation, right? When it will arise? It will arise when the components of velocities along the surface, if are same, means if the components of velocity along the surface are same, right, then what happens? After collision anyway, the components of velocities along the normal are becoming same. If the components of velocities along the surface are already same here, why? Means because they will not change. These will not change during the collision, right? During the collision they will not change. Means we should first have the condition that the components of velocities along the surface are same. If that is there, means then, so this is what is this? This is the condition for moving together. You just make a note of it. This is the condition for moving together. Otherwise they will not move together. That sticking and moving together is only for perfectly inelastic in the head-on type. That is not a condition for perfectly inelastic in the oblique type. Oblique type, what is the condition we'll have? The components of velocities along the normal direction will become same. But when we can achieve that moving together condition, if already the components of velocities along the contact surface are already same, then anyway after the collision the components of velocities along the normal are becoming equal, right? So they can move with the same velocities. Okay, so this is the point that we have to keep in mind, because this is a confusion that a lot of students will have. Okay, now we look at a question on this. After perfectly inelastic collision between two identical balls moving with the same speed in different directions, means they have the same speed, maybe v and v, like that. Okay, but different directions they are moving. The speed of the combined mass, means collision they are now moving together. After collision they are now moving together. Okay, the speed of the combined mass becomes half the initial speed. So when they are sticking and moving together, their speed is becoming what? Half the initial speed. Find the angle between the two objects before the collision. So look at this, like this we have, let's say we have objects mass m each, identical they are saying, right? We'll take the mass of them to be equal. They are moving with same speed. Let us say the speed is what? V. In different directions. That angle between them is theta. That is what we have to find. What is our task here? We have to find the theta, right? Now after collision they both are sticking and moving with how much speed? Half the initial speed, means they are moving together with v by 2 speed. They are moving together with how much speed? V by 2 speed. Using this data we have to find, so the total mass now is what? 2m, because m and m moving together. Using this information we have to find what is the theta value. How we can find? Think about it. Can we use the conservation of momentum? We can use it, right? Because initially the momentum of this is what? mv. They are at an angle theta. So initially the resultant momentum is a vector. Resultant momentum means what? Root of mv square plus mv square plus 2 into mv into mv into cos theta. So what is it? Root. This is like what? 2 into m square v square, 2 into m square v square cos theta. That is the initial momentum. What is the final momentum? That is what? mv. Conservation of momentum means what? Whatever the initial momentum is equal to final. That's it. We will get the answer. So here our task is what? To find the theta, right? What is our objective here? We have to find the theta value. Now mv is equal to this root square on both sides. M square v square is equal to 2m square v square plus 2m square v square cos theta. Bring it to the left. That will become negative, right? Actually here itself, right? We can cancel m square v square on both the sides. Here itself what we can do, we can cancel the m square v square on both the sides. Cancel it, what we will have? If we cancel the m square v square means on both the sides, what are we going to have? 1 is equal to 2 plus 2 cos theta. Bring it to the left means 1 minus 2, that is minus 1. That means what? Minus half is equal to cos theta. Minus half is equal to cos theta is minus half, means theta will be equal to what? 120. What is cos 120 minus half, right? Cos 120 is what? Minus half. Now you may think, why are we not giving general angle? Because remember, angle between two vectors will be always within the range 0 to 180. Because cos theta is equal to minus half means the angle between vectors will be always in what range? 0 to 180, right? In that we have to pick up. So cos 120 is what? Minus half. So the angle between the two objects, right, before the collision must be what? 120. Okay. So this is about the discussion of oblique collision. In the next class, right, we will look at another independent event. So one is the collision, second one is the explosion. Okay, both are independent events or isolated events where we will be able to apply the conservation of momentum principle. Okay, so next class we will talk about the explosions.